This is a video on time dilation as part of the HSC Physics course for Module 7, The Nature of Light. No matter how many times I teach this or how many times I go over this, I just get the same thrill. It's absolutely amazing how Albert Einstein, German-American theoretical physicist of the 20th century, in 1905, he published a series of papers. He called it his miracle year. One of the papers was on special relativity. And the title of the paper is called On the Electrodynamics of Moving Bodies. And what Einstein realized with this, so he came up with two postulates, two basic assumptions. The first one was the principle of relativity. And the principle of relativity quite simply states that the laws of physics are the same whether you're in a stationary, if you're stationary, let's say you're in a car, or if you're moving in that car at a constant velocity, constant speed, v. In other words, if I was to blindfold you and pull you in either of these cars, and let's say give you some earmuffs, so block any noise from the outside, you would not be able to tell in principle whether or not you were stationary, not moving, or moving at constant speed. One of the remarkable consequences of reality. And that's called the principle of relativity. So if you do an experiment, let's say you throw a ball up and down in either of these scenarios, that ball will follow the same laws of physics. It'll come back down, okay? So that's the principle of relativity. And these two frames of reference, so a frame of reference is basically like a coordinate system. We all have a coordinate system where we measure things in space, right? So think of the X and Y axes. There's also another axis, the Z axis, think of the page that comes out of the page. So we're usually familiar with the X and Y axis in maths. So left, right, up, down, but there's also back and forth, and that's the Z axis. So these two frames of reference, they're known as inertial frames of references. Inertial comes from the word inertia, from Newton's first law of motion, which states that an object that's stationary or not moving, or an object that's moving at constant speed, will remain doing so unless acted upon by an external force. So in other words, if you leave things as they are, they'll continue doing whatever they're doing. So that's the principle of relativity. In all inertial frames of reference, the laws of physics are the same. And the second one, the constancy of the speed of light. Okay, the constancy has got the word constant, which means the same, stays the same. In other words, Einstein said that the speed of light is the same for everyone. We all measure the same speed of light. It's the universal speed limit. Nothing can travel faster than light. And light travels at 300,000 Ks per second. Incredibly fast. So the two postulates that Einstein came up with, principle of relativity and the constancy of the speed of light. Now, in his 1905 paper called On the Electrodynamics of Moving Bodies, in that paper where he talks about special relativity, so special because it only applies to inertial reference frames. There's general relativity and special relativity. Special relativity is examinable in the HSC. General relativity is beyond the HSC, it gets more complex. So special relativity is relativity only dealing with inertial reference frames. One of the consequences of his work on special relativity was what was known as time dilation. I'm about to show you using very simple maths, so nothing more complex than Pythagoras, really, and a bit of algebra. You can arrive at a remarkable result. And this isn't really the result the derivation that Einstein came up with, but it's just a simplified way of showing where he got to in terms of time dilation. For the HSC, you don't need to know the derivation. It's just nice to know where it comes from. And like I said, it's a remarkable feature of reality. It's something we don't really think about in everyday life. If we go back to Newton and the classical physicists, before the 1900s, before the year 1900, Newton believed that time and space were absolute or constant, in other words. So Space and time, the space and time we measure, we experience every day is the same for all of us, regardless of if we're stationary or moving at constant speed or accelerating. But the speed of light was believed to be different for everyone. So the speed of light changes for everyone. If you're moving, if you're stationary, the speed of light's different. Einstein came along and said no. He said the exact opposite. Time and space can vary. They can change. And the speed of light is constant. So in other words, your time and my time are different. What we measure, what we perceive as time. We have biological clocks, and our clocks run at different rates. And we measure things in space differently. They give different results. Let me show you how. So I'm going to start with a very simple thought experiment. A thought experiment's a hypothetical experiment. I hope you can follow along with this. If you're a junior science student, I hope this really enlightens, engages your brain and really gets you thinking about reality. Let's consider a spaceship. Here's a poorly drawn spaceship moving along at some velocity v. So velocity just means speed in a particular direction. So it's moving to the right in this case, let's say. There's a guy in a spaceship, let's say it's me. And there's someone, let's say one of my students, on the ground who's watching me. So far there's nothing mysterious. Spaceship moving along and I'm on the ground standing watching it. Now let's add two mirrors. So suppose I add two mirrors and I've got a light beam that's moving between the two mirrors. Let's call that mirror 1, mirror 2. So the light beam can bounce back and forth. When it goes from the top to the bottom and back to the top, think of that as like a tick on a clock. So I'm going to do an experiment to see how me and the observer that's watching me perceives this light beam, and whether or not we actually measure the same time for this light beam to give a tick, to give a pulse. So suppose the guy on the ground, the observer, let's call his time t, and let's call my time t dash or t prime. In physics, we use prime or a dash to indicate, to indicate another frame of reference. So there's two frames of reference here. What do we hear? T dash. There's a frame of reference of the spaceship and the frame of reference of the person that's stationary watching. Now here's where it gets interesting. So the person on the ground, the observer, will notice this. So as the spaceship moves a bit more in space, use red. Oh, actually, let's consider the mirrors for now. He's going to see this. So the observer on the ground will actually see this. Now the person, think of it, this is where you've got to think outside the box with relativity. It can get complicated very quickly, but if you just imagine this, like Einstein, it could make a lot more sense. Suppose you're the person on the spaceship. Now, according to relativity, you're actually stationary relative to the spaceship because you're moving with the spaceship. When you're driving in a car, you're sitting in a car, you're actually stationary. You're not moving with respect to the car. That's relativity. So on the actual spaceship, you're seeing the light beam go up and down. However, the person standing on the ground watching the spaceship will see it do this. It'll move in a zigzag, diagonally. And that's because the spaceship is moving to the right and the light beam is also moving too, right? I'm sure you'd probably see this you can do this on a train as well, if the train's fast enough. Train and you're on a platform, have someone on the train and do an experiment where the person on the train is throwing a ball up and down. You'll be able to notice this effect too. The ball will actually look like as though it's moving diagonally, even though it's not, according to the person on the train. So that's relativity. According to relativity, both observers will have legit accounts of what's happening. Both have perfectly legitimate accounts. The guy on the spaceship will see the beam go up and down. The person on the platform or the person on the ground will see it go diagonally, and both are actually correct. Okay, because that's what you see. Let's call the diagonal distance here d dash that the light travels. And let's call the distance between the two mirrors d. Let's now take this and use black. Let's take this d here. Let's translate it. Translate means move in space. Let's move it here. Let's call that d. And the d dash, let's move it here. And let's call this here d motion. D sub motion. Okay, this is the distance the spaceship travels, right, along the x-axis. Let's call this the x-axis here. Okay, so we have d, the distance between the mirrors that the person on the spaceship sees. D dash is the distance between the two mirrors that the light beam travels between. And d sub motion is the distance the spaceship travels. Let's draw a right angle here. We can make this a right angle triangle. Let's use another result. V equals d over t. Velocity, v, okay, or speed, is d distance. Okay, for argument's sake, let's call v speed in this case. Okay, speed, distance over time. Okay, speed is a measure of how much ground, how much distance you cover in a certain amount of time. Okay, and typically measured in meters per second or kilometers per hour. So let's use this result. Now for light, light's quite interesting. We replace the speed v with c. C is the light at which the speed at which light travels. C is actually Latin celeritas. I think that's how you spell it. It means swift. Okay, we use C. C is a number. It's 3 times 10 to the 8 meters per second. So 300 million meters per second. Okay, that's C. Now we can rearrange for D. D is just CT in this case. Okay, C is a number. Let's use Pythagoras. Let's take this triangle here, and the hypotenuse is d dash, and let's write the following expression. So I hope you can follow along. D dash squared is d squared plus d motion squared. You're going to see how powerful this statement is. Just a simple statement, Pythagoras. C squared is a squared plus b squared. It's a right angle triangle. Now, let's substitute in for d dash squared. Now, d we established is ct. So to put in CT. Now in this case, you have to be careful. There's C prime squared, T squared. Now there's no dashed. Actually, don't worry about the dashes. There's no dash for the T or C. If you recall, the D dash is what the guy on the ground sees as T. Right? He's looking at what's happening and he's measuring the time in terms of T. So it's T. And that's equal to d squared. Now d squared is c squared t sub naught squared. Okay, should be t sub naught, my apologies. T sub naught. T sub naught is the time measured by the guy on the spaceship that's moving relative to the guy on the ground. Plus, so d sub motion is just v squared t squared. Okay, because for speeds less than the speed of light, d is just vt. So replace the c with a v. Okay, and d squared is just v squared t squared. That's where I got that from. Okay, same thing for these guys. Nothing mysterious here. Just substituted in some facts that we know. Now, let's divide both sides of the equation, because equations, whatever you do to one side, you have to do to the other side. Let's divide everything by c squared. Okay, you can do that in maths, because so long as you do it to one side, you can do it to the other. Divide everything by c squared. Now, c squareds cancel out here. And we're left with this. T squared is t sub naught squared plus v squared over c squared t squared. Let's tidy up this mess, use some algebra. Let's take the t sub naught squared. I should say, let's take this guy over to the left-hand side. Let's neaten it up a bit. T squared minus v squared over c squared t squared. T sub naught squared. So let's factor out the t squared. So it's just 1 minus v squared over c squared. We're pretty much done. Let's take the square root of both sides. When you do that, the squares cancel out, because square and square root are inverse operations. They cancel out. You're left with this. 1 minus v squared over c squared. I should say the square root 1 minus v squared over c squared. And here's what we arrive at. Absolutely remarkable. 1 minus, t naught, 1 minus v squared over c squared square root. This over here, ladies and gentlemen, is a remarkable result. It tells you that the times experienced by the guy that's not moving on the ground and the guy that's moving on the spaceship are different. We all experience different times. The faster you move, the slower time goes. This quite simply tells you that moving clocks run slow. We all experience this every single day. It's not noticeable for speeds much less than the speed of light. So V is much, much less than the speed of light. It's not really noticeable. However, if you're moving quite close to the speed of light, let's say rockets blasting off into space, you will notice this. If you had an accurate enough clock, you could actually measure the difference. So T is not equal to T sub naught. The two times are not the same. They're related by this expression. And it's the denominator. The square root of 1 minus V squared over C squared. This has a special name. This is called, they give it a name in relativity, the Lorentz factor, named after Hendrik Lorentz, Dutch mathematician, also known as the gamma factor. This pops up everywhere in relativity, special relativity in particular. Okay, gamma. This thing is what makes the two times different. Let me show you something. Let's suppose, so T, as we established, is the time. So this is my time. This is what I see. This is the time I see experienced by the spacecraft. And T sub naught is the time experienced by an observer at rest relative to the spacecraft that's moving with the spacecraft. T sub naught is called, also known as the proper time. The time you measure in your reference frame is called the proper time. Let's suppose you could move at the speed of light. So let's suppose the V squared becomes 300 million squared divided by the speed of light, 300 million squared. Remember, V squared over C squared? Here's what happens. This here is equal to 1. It's the same thing. So 1 minus 1. So 1 minus 1 is 0. The square root of 0 is 0. And time, this doesn't make sense mathematically. Anything divided by 0 is undefined. So what you see, if the spaceship can move at the speed of light, you would say that you get a ridiculous answer. You wouldn't even be able to see the spaceship actually, because of something called length contraction. So time becomes warped and it won't make any sense for something moving at the speed of light. Okay, it's actually impossible for anything with mass to move at the speed of light. Light moves at the speed of light because it's massless. So the light from the Big Bang, around 14 billion years ago, never experienced time at all. It's ageless. And it's been flowing throughout the universe ever since. So it doesn't really make sense for something to have mass to move at the speed of light. It's undefined. Okay, can't really measure time in this case. That's what that means. And that's special relativity. So moving clocks run slow. Let me do an example to illustrate this, an actual example. Let's suppose you have astronauts. So an astronaut moving at a velocity, at a speed of, let's say, 70% the speed of light. That's what that means. 0.7 times C. If you work it out on a calculator, 0.7 times 300 million, you'll get 70% the speed of light. So let's suppose an astronaut's moving at a velocity of 70% the speed of light to planet X. Now an observer, let's say I'm an observer on Earth, measured that this journey would take, I don't know, let's say 5.25 years. Now, according to the astronaut, how long will this journey take? Now, from everyday intuition, you would assume you would say that it'd be the same. 5.25 years. We're going to say that this isn't the case. So how do we do this? We need to use the formula, time dilation formula. T is T naught over the square root of 1 minus V squared over C squared. Let's start there. Now we're interested in T sub naught, okay? Because T typically is the observer that's watching something move. T sub naught is the astronaut. This is on the HSC formula sheet, it's given. You just need to know which is which. So we're interested in T sub naught. We need to calculate T sub naught. So rearranging using algebra, it's just this. Okay, T sub naught, take this denominator, multiply by T, algebra. So what do we have? Now T, we know is 5.25 years, according to the guys on Earth, the person on Earth, times the square root of 1 minus, now, 0.7 times the speed of light. So 0.7 c squared over c squared. Okay, v squared over c squared. Now the c's cancel out, so you're left with 0.9 squared, 0.7 squared. I'll show you why in a sec. Okay, because all of this squared is just 0.7 squared times c squared from maths, basic maths. So you're left with this result here. So punching this into your calculator, you'll get this 3.75 years. I'll put 2 decimal places. Look at this number. Compare this number. So the astronaut will feel that the trip took 3.75 years. The person on the Earth, 5.25 years. That's time dilation. Faster you move, the astronaut's moving quite a fast rate, fast speed. The faster you move, the slower time appears, okay? Both observers, now it's very important to stress here, special relativity. Both observers are actually right, no one's wrong here. It all depends on your reference frame of reference. Okay, everything's to do with relativity. It's always with respect to something. Astronauts moving with respect to someone on the ground, and someone on the ground is moving with respect to the astronaut moving in a spaceship. So moving clocks run slow.